In sections 9.6 and 9.7, we're going to look at some specific application problems where we can use the differential equations we have built to answer some questions about some very important ideas. First we're going to look at is looking at two populations of species at the same time. We're going to see how they interact with each other. We looked in the first few sections of this chapter looking at the population of maybe one species and how it may grow over time or decrease over time. But in a more real-life situation, there may be more than one population of species that affects each other. So what we're going to have here is not just one differential equation, but two differential equations that both have to do with the same variables. We're going to have the variables be the population of the first species and the population of the second species. There's lots of different interactions that could occur between these, but we're going to focus on three main kinds. One is that two species are in competition over food, so that means that they both can't coexist and both can't grow so much at the same time is because they're both fighting over a resource. There's the predator-prey situation, which is that one population benefits from eating another population, and it has a certain dynamic we'll focus on. And then the third is that two species may be helping each other out. It's because they both thrive, that they both continue to grow because of that. That's what we're going to call symbiosis. So each of these situations and more situations past this have the same basic concept that we're going to go over here. In the book, they go into a big example with robins and worms. That's the predator-prey situation. And they go through all of these steps with that example. And if you want to go through that, it's good to have that there. We're going to go through the exact same steps, but we're going to focus it on a different situation. And that is going to be the food competition example. So the reason why we're using a different situation here is just to show something different, but it really is the same work we're going to be going through as the book does with the robins and worms example. So here's our example. In some environment, we're going to have two different species, bison and elk, and they are both going to be eating grass. That is the resource that they are going to be competing over. We're going to build these differential equations from the ground up. We're going to try to understand where it comes from. And then in the next video especially, we'll talk about things we can do with those differential equations. So first, we're going to look at the population of the bison and the elk separately, as if both of those species weren't there at the same time. So without any influence from the elk, the bison's population grows at a rate proportional to its population. We're going to say with a constant of proportionality A. So this is exactly what we've done in previous sections in this chapter. We can just say that the population of bison is going to grow exponentially. It's going to grow at a rate proportional to its population, and that is without any influence from some other kind of source. In the same way, without any influence from the bison, the elk's population grows at a rate proportional to its population. This is at a different rate than it would be for the bison probably, so we're going to call that constant B. We're going to let B, capital B, be the bison's population, and capital E be the elk's population. So let's maybe put that down. Capital B is the population of bison at time t. This is like saying this is B of t, it's a function. And same thing, we're going to have E is going to be the population of elk at time t. And we're going to call that E of t. It's a function E of t, and that's our solution to our differential equation, our capital B and capital E. All right, so that's simplistic, and that's what we've dealt with so far in this chapter. But now we're going to say both of these populations exist at the same time, and they have influence over each other's population because they're competing over the same resource, and that being grass in this case, what they're eating. So to take into account the interactions between the population, we're going to have this terminology of something called an encounter. So in this example, an encounter is going to be the elimination of 1 acre of grass, or it's going to be 1 unit of grass is going to have to be an encounter. So that is that the resource that both these populations are competing over is being depleted, and each encounter that we have, we're going to deplete 1 unit of resource. And this could be by either population or by both populations or just by one. It's just in general, one thing at a time. To look at what an encounter situation is in the other two examples, a predator-prey situation, an encounter, and this makes a lot more sense in this case, is when a predator kills a prey. So that is when those two populations are encountering each other or interacting with each other in what we're talking about, predator eating prey. In a symbiotic relationship, in symbiosis, an encounter would be the thing that encourages the growth of the both populations. So the example we'd like to go to is if you look at the population of bees and flowers, when a bee pollinates a flower, it encourages the growth of the bee, it encourages the growth of the flower because it spreads the pollen of the flower to other areas. So each time that occurs, that would be an encounter. Now this idea of encounter could be used for any kind of context, but that's what we're going to sort of focus on. And note that we're not really going to need to know exactly what an encounter is in any of these situations, but to help us see where these differential equations are coming from. So in all three of these ideas, with the competition, the predator-prey, and the symbiosis, the number of encounters grows at a rate proportional to the product of both populations. So this is going to be the same for all these types of interactions. And we're going to try to see kind of how that works in a second here. So as more grass is eaten, less is available for others to eat, and this inhibits the growth of both populations, although it may be at different rates. So again, as both the populations grow, the resource gets depleted, so that has some kind of factor on how much these populations can grow. So we're going to let C and D be different constants of proportionality relating to this encounter idea. And we're going to have negatives here in the differential equations because as those populations grow, there's a negative effect to how much the population can grow further. There's some inhibiting factor with the resource. To go back to a second to this idea of the number of encounters grows at a rate proportional to the product of both populations, we can think about number of encounters is basically how much grass is eaten, how much grass is available in that environment. And we can say that it depends both on the population of the bison and the population of the elk. We think about as the product of both populations is they're both interacting with each other, and that's what we're saying here. It's not just one or the other. So here are our differential equations that we're going to be dealing with in this chapter. And all of our interactions are going to look similar to this, and we're going to see soon that it really is the signs, positive or negative, on each of these terms that's going to determine what kind of interaction we have. So, as I said, it's the signs of the constants of proportionality, or we can think about the signs in front of each term. Both of those are kind of the same idea. Determine the growth and what kind of interaction we have. So let's just say it in general. Let X and Y represent the population of two species, and let all constants of proportionality be 1. So we're going to kind of ignore this idea of different rates, and just for simplicity, this is just for simplicity's sake. So we can try to get the idea down so we can look at more complicated examples later on. So our first kind of interaction, food competition, has our differential equations we had before. We have the X and the Y here are the idea that we are growing at a rate proportional to our population, that without these encounters, both these populations will just be growing. But they also both have a negative effect when they encounter each other because their resource is being depleted. So now let's look at the predator-prey situation and see how that might look like. So in the predator-prey situation, we have that for one species, if you look at the other species and they don't exist, this is like X is the predator this is x equals the prey, and y is the predator. So if x is the prey, if the predator doesn't exist, their population is going to go up, right? They have nothing inhibiting their growth. It's just they're going to continue to grow. However, on the other hand, the predator, without any influence from the prey, without any prey available, their population is going to decrease because they don't have food. So without the other, one of them grows and the other one decreases. And then we think about the interactions between them. The number of interactions is the number of times a predator kills a prey. For the prey, this is going to decrease their population because they're the ones being killed. And then for the predators, this is going to increase their population, right? Because every time something's killed, they get food, and this encourages their growth. So we have these two differing kind of differential equations, but again, what's different is the signs, positive, negative, in front of those terms. And now let's look at symbiosis. So this is both populations encourage growth for each other. So that is without the other population, this first term, both of these populations would decrease. If you think about bees and flowers, without the flowers, the bees won't have the resource they need to survive, so they're going to decrease in population. If the flowers don't have the bees, they have nothing to pollinate themselves across the landscape, so their population is going to decrease as well. The amount that it decreases depends on those constants of proportionality. It may be by a lot, it may be by a little, but that's the difference in the differential equation. And then both of those populations are going to benefit from the number of interactions. So as the number of encounters or interactions increases, both of those terms are going to be positive and population goes up. So we've talked about where these differential equations come from a little bit, try to understand what they're doing. A major focus of this section is just looking at differential equations and trying to understand what's going on. Then we can go back through everything we've learned in previous sections and talk about what can we do with these differential equations. We can think about solutions to the differential equation. We can think about plugging in values. We can think about initial value problems. In the next video, we'll look at a couple of different examples of things that we can do. Also note that both of these sections, 9.6 and 9.7, are fairly short sections, so they're not going to have a terrible amount of example problems, but we're not going to do a terrible amount of problems together. And lastly, there is a chunk in 9.6 that has to do with phase planes and slope fields. And this has to do with a section that we skipped, 9.3 in this chapter. So everything that has to do with those ideas is cut out from the material in this course. In the next video, we'll look at some practice problems related to these differential equations.